Hello everyone. I'm in my studio, so excuse the mess, and I lost my voice. So excuse me on that as well. But this video is going over everything that I believe you should know about linear functions. So let's get started. First, we have to think about what is a function. Function is sort of like a defined relation between two or more vectors. Remember, when we're trying to formulate or relate different factors together, we obviously need more than one, right? We probably need two minimum, correct? And a lot of times these vectors are changing. So we call these variables. And oftentimes we use different alphabets to represent these variables. Again, these are unknown values or changing values, right? So essentially, when we're trying to formulate a relation between two variables, let's say the commonly known variables x and y, that would be considered a function, you would think, but we have to be very careful because not every relation can be a function. So that's what we're going to talk about first. What kind of relation makes a function? Again, function is a relation, right? But as you can see in this lovely mind map, sort of very simple mind map that I drew, not every relation is a function. Every function is a relation, but not every relation is a function. So let's give it an example. This is a bit of a disgusting example, but I find this to be the most effective. So let's imagine we have Ryan, because I used Ryan as my little guinea pig yesterday, so I'm going to use Ryan again. Let's imagine Ryan eats different colored candies. So let's imagine that Ryan has pink candy. When Ryan eats pink candy, he gets pink poop. When Ryan eats yellow candy, Ryan gives yellow poop. And Ryan eats blue candy, Ryan gives blue poop. And you think, okay, that makes sense. That's very straightforward. What Ryan intakes, Ryan, leaves out, right? But what if, let's say, he eats a white piece of candy and he gives out black or red or white poop? If that's the case, then that white piece of candy is producing endless, I wouldn't say endless, but multiple possibilities, right? Multiple outcomes. Now, this relationship, or this relation, I should say, is not considered as function. Why? Because there is that white piece of candy that could produce three outcomes, and we don't like that. We want to make sure that if we have a certain input, we have a clear output. But over here, we cannot be 100% sure whether he's going to give us black poop, red poop, or white poop. So in this case, this is not a function. But let's imagine our lovely Dorothy wants to play a little detective. So this time around, instead of looking at what color candy Ryan eats and then looking at his poop, we reverse the order. So in this instance, our input would be the color of poop, and our output or our outcome would be the color of candy. So same thing, when we see pink poop, that means Ryan ate pink candy. When we have yellow poop, that means Ryan had yellow candy. When we have blue poop, that means Ryan had blue candy. And then if I see him with black poop, then we know for sure that he had white candy, 100%, right? When the order was reversed, for instance, when our input was white candy and our output was when our input was white candy, we didn't know what the output would be clearly. However, in this instance, having black poop clearly means he had white candy, right? Same thing, when he had red poop, that means he had white candy. And if he has white poop, that means he had white candy. 100% for sure, right? It doesn't matter whether the poop was black, red, or white. We know for sure, 100% that he had white piece of candy, correct? So therefore, in this case, when each input has clear output, this relation would be considered a function. We know that in order for us to have a function, we need to make sure that every input comes with a clear output. So that means an input with multiple outputs is not a function, but multiple inputs that give one same output is okay. That's a function. So we just talked about input and output. We call a group of input values, and again, usually these are represented by variables x and y. They don't have to be. They can be anything from A to Z. Yeah, x and y are just common variables that we use. So let's imagine that x represents a set of input values. We call this set of values domain. And y, let's say, represents output values, and we call a group of output values range. And since we know that every input comes with an output, now, I did not say that this input-output relation necessarily has to be a function, but if, let's say, with an input, there's an output, then we have what we call an ordered pair. So now let's combine our knowledge about ordered pair and our knowledge on function and determine if a set of ordered pairs would be considered a function. So here's an example. I have 6 ordered pairs or 6 coordinate points, right? If we were to plot them on a coordinate plane or a Cartesian plane, but we'll get into that in a little bit. But first, in order for us to determine if this set of ordered pairs would make a function, what I'm gonna do is use what we call mapping diagram. So what I'm gonna do is create a little pocket. I'm gonna create 2 pockets, and one pocket is for domain. Remember, domain is the set of input values, so our x values, right? So I'm gonna put x. And then in the other pocket, I'm gonna go ahead and put y, my range or output values. And what I'm gonna do is I'm just going to list all the domain, so x values into the domain bag and all the y values into the range bag. And what I'm gonna do is now do a little bit of a Cupid's bow thing and match up all the ordered pairs. So we have 1, 5. So 1 matches up with 5 and 2, 7. So 2 matches up with 7 and 3, 0. 3 matches up with 0. 4, 4. 4 matches up with 4. 5, 0. 5, 0. 3, 1. 3, 1. And see, now thinking about what relation can be a function, remember, in order for us to have a function, we need to make sure that every input has a clear output, meaning we could have one input giving one output. Obviously, that's okay. But one input giving multiple outputs, that is not okay. Why? Because we want to make sure that we are 100% sure on what output we're going to get with one single input, right? But if you take a look at, let's say, 3, when I put 3, I don't know if I'm going to get 0 or 1. It's unclear, right? So therefore, this is not a function. Okay, now let's take a look at another example. This time I have 1, 1, 5, 1, 7, 1, 0, 1. And let's go ahead and create another mapping diagram. So I put all my domain, over here on one side, and then I put all my range, and we only have one value for range, which is y equals 1. So again, if I were to go ahead, do another Cupid's bow thing, I can match them up like so. And now in this case, you're right, not every input comes with a distinctive output, in a sense that it's not like, oh, one input gives one output. It's not like that, right? So it could get a little confusing. But no matter what, even if our y value is repeated, I know for sure 100% that when I put in 1, I'm gonna get 1 as my output. And when I put in 5, I'm gonna get 1 as my output as well. Same goes with 7 or 0. So therefore, this is a function. So again, this could be very confusing, but always remember that we wanna make sure, as long as we know what our output would be for that input, 100% sure, then it's a function. Even if it means there are multiple input values producing one single output value, because we know for sure that each one of these values would lead to one clear output. I don't know why I did air quotes. No air quotes needed. One output, therefore we know that that relation would be a function. But mapping diagram is only one really convenient way of visualizing a function relation. Another more commonly used visual representation of a function is using our coordinate plane, or Cartesian plane, so we call it. So we know that a coordinate plane is made up of two number lines, one horizontal, and one vertical, V, so vertical. So I'm going to go ahead, draw my coordinate plane like so. By the way, just in case, if you're not sure, let's do a quick revision. So we call this coordinate plane. Right? Or also known as Cartesian plane. And as you can see, because of the two number lines that we have, we decided to go ahead, put our horizontal number line as x-axis. So all the x values, so domain, would exist on this number line. And all the range, so y values, would exist on my vertical number line. And they intersect at one clear point, when x is 0 and also when y is 0. Yeah, kind of like a belly button. We call this point the origin. Okay. And as you can see, we have 4 different sections, right? And it goes counterclockwise. We decided to go ahead, name each one of these 4 areas quadrant. So it goes quadrant 1, quadrant 2, quadrant 3, and quadrant 4, right? So in quadrant 1, all the x values will be positive, and all the y values would be positive as well. So we know that when a coordinate point is in quadrant 1, x is positive, y is positive. When our coordinate point is in quadrant 2, now our x value is no longer in positive section of the number line, but it is on the negative, correct? But our y value is still on the positive. So all the points in quadrant 2 would have negative x value and positive y values. And in quadrant 3, again, our x values would be all negative, but this time our y values too would go into negative, like so. So in this case, in quadrant 3, our coordinate points have negative x and negative y value. And finally, in quadrant 4, as you can see, our y values are all on the negative side, but our x values are all on the positive side. So therefore, when it comes to quadrant 4, we would have positive x value and negative y value. So I just wanted to go over some fundamentals of coordinate plane before we proceed. So now let's go ahead, use the order pairs that we had in the first example to go ahead, plot them in our coordinate plane. So we have 1, 5, so that would be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 5, very good, 2, 7, 2, 2, 7, 3, 0, 4, 4, 4, 1, 2, 3, 4, 4, 5, 0, and 3, 1. Now, let me ask you a question. Why do we have points instead of a line? Well, it's because, remember, a line is made up of many points. So if I were to give a line, that means all the little values in between the big points. For example, if I were to put a line between 1, 5 and 2, 7, 1, 5 and 2, 7, like this, what that means is when x is 1.09, I'm gonna have a y value. When x is 1.57, I'm going to have a y value. But that is not the case, right? They specifically gave us that when x is exactly 1, when x is exactly 2, we are going to have exactly 5 and exactly 7, correct? So therefore, we are saying, hey, these are the specific values, not all the tiny values in between that would essentially create a line. Okay, so now how are we going to test out to see if this relation is a function? Now, what we do is what we call vertical line testing. Vertical line testing is pretty straightforward. We simply draw series of vertical lines through each one of the coordinate points and see if there's an overlap, like this. I'm gonna go ahead, draw one vertical line through the very first point, 1, 5. I'm going to draw another just straight vertical line through 2, 7. And then I'm going to go ahead, draw clear straight line through 3, 0 and 3, 1. Another straight line through 4, 4. Another straight line through 5, 0. Now, each one of the lines should have only one coordinate point sitting on the vertical line. So I have one here, so that point passes the vertical line testing. I have another point over here, so which is 3, 1, and there's a little bit of problem. I have another point, 3, 0, so I have two coordinate points sitting on that one vertical line. So therefore, this plot, I guess this set of coordinate points does not pass the vertical line testing. Therefore, it's not a function. Does not pass the vertical line testing. Therefore, not a function. Let's go ahead, apply the same idea onto the second example. Now I'm going to go ahead do the vertical line testing. So I'm going to draw a vertical line through each one of the coordinate point. Only one coordinate point per vertical line. And this is what we like, right? So this passes a vertical line testing. So therefore, it is a function.